Today, we're going on an adventure deep inside the neural network to uncover the magic of backpropagation. Imagine a student taking a test. They make mistakes, and their teacher, in our case we call this one loss function, helps them learn by pointing out errors. The student then adjusts their study habits accordingly. That's exactly what backpropagation does in a neural network. The more we practice, better we get. Just like a neural network getting better at making predictions. Let's break it down and see how each piece of the network contributes to this learning process. Let's first start with the dense layer, as you can see in here. This is actually the thinking unit. So our journey begins with the dense layer, which acts like a collection of neurons in our brain. So each neuron connects to the next layer through weights and biases. So let's see how it works. Let's first have this forward function, this one. This is where inputs are multiplied with weights and adjusts with biases to produce an output. So here, as you can see, we have the plus and we also have the input that so we do the multiplication. We have the backward function. So during the backward, it calculates the ingredients needed to adjust the weight. Let me highlight this one first. Think of this as a student realizing which topics they got wrong on the test and deciding to study them more. So the weights are like a student's memory, retaining what they've learned and adjusting based on feedback. The biases add a slight nudge to ensure the network doesn't become too rigid and can still generalize well. So without the dense layer, the neural network wouldn't be able to transform and combine inputs effectively. That makes it a crucial component in learning. So that's how effective and how important the dense layer is. So let's move on to the next part. We have the value activation. Let's say and call it as the filtering part, or filtering the important stuff. So after the dense layer, we reach the value activation function, this one. Anyway, when I say function, it's actually a class, so I will just be telling you if it's a class. So again, when I say function, refers to the whole code that pertains to a certain class, or it could be a certain function. The value activation function acts like a filter because it keeps only the positive values, again, only the positive values, and any negative value is discarded, just like a student ignoring incorrect study methods. So during the forward function, here, negative values become 0 and positive stay unchanged. And so also during the backward function, during this function, it helps adjust only the positive contributions and ignore the rest. So think of this as a teacher emphasizing the correct parts of an answer and ignoring the noise. So if we didn't have value, our model might get stuck and stop learning since negative values wouldn't contribute properly. It's just like there would be a lot of people inside the room, but only those very few are your students or those who are getting the correct answers, and others are just, shall we say, noises or noise. So by filtering out unnecessary information, value keeps the learning process efficient and prevents unnecessary complexity. So again, this function is essential for ensuring that our neural network captures and emphasizes the most relevant patterns in the data. Let's move on to the next one. We call this one the softmax activation. Again, softmax activation or the decision maker. So during this part, softmax activation function helps the neural network. Alright. Again, it helps the neural network make decisions by turning outputs into probabilities. If 3 doors represent different career choices, softmax tells us which door is the best option or the best bet. We have here the forward function. Alright. So what is happening in here? So forward function turns raw outputs into possibilities or probabilities, making the highest one stand out. So backward, on the other hand, this one, alright, so calculates the probabilities, or it calculates how the probabilities should be adjusted when learning the mistakes. So you can actually set the value or how it is to be adjusted. There are different ways on how to make some adjustments into your calculation. So softmax ensures that the network's final decision is interpretable by assigning a probability score to each possible class. So what would happen when there is no softmax? So without softmax, our model's predictions would be meaningless numbers instead of clear, actionable probabilities. So with that said, we can say that it plays a crucial role in classification problems because it ensures our network can confidently pick the right answer. So what about the loss function? We have here the two classes. In our case, in comparison to being a teacher, this is actually the teacher's feedback. So it tells you which one is good, which one is not, which one is correct, which one is wrong. We meet our categorical cross-entropy loss. The tough teacher points out mistakes. So this function actually calculates how far off the predictions are from the actual answers. So how good the student is, how bad the student can be, how intelligent the student is with respect to a certain subject of a certain class, how good he is. So forward function measures the difference between prediction and the real labels, this one. So based on the results, we have the predicted value, we have the real value. What's the difference? When the difference is so big, then your prediction is very far from the reality. Then we have the backward. So gives each layer a nudge in the right direction. So it ensures they don't make the same mistakes again. So this is just like a guardrail. I already have learned something from my mistakes today. So by next time I'm going to get the test, I won't be committing the same mistake again. So by that time, possibly I would have it correctly. So the loss function helps our model understand how confident it should be in its predictions. So a high loss means the model is performing poorly, while a low loss means it is getting closer to accurate predictions. So without a loss function, our neural network would have no way of knowing whether it is improving or not. It is actually the metrics that you can use to tell yourself that you're doing well with respect to your modeling, or if you are bad at modeling, or what kind of adjustments you're going to do. Are you going to add more parameters? Are you going to add more data, or what? Then the backpropagation process. So after everything having been discussed, so let's go to this one, because this actually has the whole process, the learning process from the very beginning until the end. So now let's tie everything together. The key learning process in a neural network happens actually in 5 steps. We have the dense layer, which does the matrix multiplication and passes values forward. Then we also have the ReLU activation function, that keeps only the important positive signals. And then we have the softmax activation here. This converts final scores into probabilities. And then we also have the categorical cross-entropy loss, this one. So this calculates the error. And then the error is sent back through the network, which means it is sent back, it backpropagates, right? Now you can get the meaning of backpropagation. You now have the results, then something is still not going on well, then your model relays the mistake to the first part, and then it's going to process again and again. So it updates the weights and biases. So backpropagation is the key to adjusting our network based on past mistakes. So each layer here sends information backward so that earlier layers can learn from the final output, and then the entire system works like a chain reaction where each layer fine-tunes its setting based on what the previous layer has learned. And this iterative process is why neural networks become smarter over time. So it adjusts themselves to become more accurate. Let's take a moment to analyze our model performed during the training. So as you can see here, the different iteration, and also you can see the loss and also the accuracy. So initially the model had a high loss and low accuracy, so meaning its predictions were almost random. As training progressed, the loss decreased, so from 0.66 now it is 0.31. Now the accuracy rate is higher. So as the training progressed, the loss decreased significantly, so when the accuracy quickly improved, that shows that backpropagation effectively tuned the weights. By around 2000, the accuracy actually reached 94%, and then after that, further improvements were minimal. That indicates that the model had learned most of the patterns in the data. So this stability suggests that the network converged well, meaning additional training beyond this point may not significantly enhance performance, because actually from this iteration 4000, there is no additional minimal amount of accuracy being added, so which means there's no more significant data or learning that's being added to the model. And there you have it. Backpropagation is like a student's journey, learning from mistakes, adjusting study strategies, and getting better over time. Thanks to this process, because neural networks can recognize faces, it translates languages, and it even beat humans in games. So hope you enjoyed this journey inside the neural network. Stay curious, keep experimenting, and let's build some AI magic together.